In this video, we're going to go through how to identify what the charges are for the transition metals, but also for the regular elements on the periodic table. So first up, we're going to first label the known charges on the periodic table. So we know that everything in group 1 has one valence electron. So because these all have one valence electron, they all end in S1, they're all going to be +1, always. Why? Because once they lose that outside electron, that valence electron, they're going to then be isoelectronic to the noble gas that comes before it. So if we're looking at lithium, when it loses one electron, it's going to become isoelectronic to helium. Now, you can see that hydrogen is going to be an exception to that, right? Because once it loses its one and only electron, it's not going to be isoelectronic to a noble gas. But for everything else in here, if it loses that one valence electron, it will become isoelectronic to the noble gas before it. Similarly, in group 2, everything in group 2 is going to be +2 because all of these end in S2. So there's only 2 valence electrons. If you take out those 2 valence electrons, all of these would then be isoelectronic to the noble gas that comes before it. So like beryllium would lose 2 electrons, go from 4, 3, down to 2, and then it would be isoelectronic to helium. Okay, these are the transition metals. So we're going to spend some time kind of going through these in a bit. But if we jump over here, boron and aluminum, they're going to be +3. And the reason for that is because they have S2 and then P1. That's their valence shell. So they have 3 electrons there. They can lose those 3 and then become isoelectronic to the noble gas before there. Now, as you move down from there, it's not going to work out because the D's are going to be in there as well. So it's not going to be isoelectronic, but they could lose that many electrons. All right. So the dividing line becomes an important thing as well as we move on. Now with carbon and silicon, these are both +4 or -4 because they can lose 4 electrons or they can gain 4 electrons. And depending on what they do, they'll either go back to the noble gas that comes before, or they'll gain to look like a noble gas that's later on. That's for those 2. The nitrogen group, these are all -3 because they just need to gain 3 electrons and then they'll look like the next noble gas. So that's -3. These will be -2. Oxygen, these just need 2. And then the last one we have here is -1, and they just need to have 1, and then they become isoelectronic to the next noble gas on there. All right, so those are the known ones. Now we're going to kind of focus on the transition metals and how to figure out those. Okay, so here we're going to go over lithium. So lithium is He, and then it's right here, so it's going to be 2s1. The orbital diagram for it's going to be He, 2s up. And what we're doing here is we're trying to figure out the possible charges. So if we take a look at this, if you took away this 1 electron, it would then be isoelectronic to helium. So that's what everything in group 1 is going to do. So that's what everything in group 1 is going to do. It's going to become isoelectronic to whatever noble gas came before it. All right. So possible charges for this would just be +1. And that's the only thing you can put in there because that's all we have. The next thing that you would have is the reason. So it becomes more stable. And you'd want to also put that it's isoelectronic to, this one's isoelectronic to helium. So that's how you would do lithium and pretty much anything in group 1. Okay, beryllium. It's in group 2. So this is going to be He2s2 And then its orbital diagram is going to be He2s up, down. Now for this one, it has 2 electrons, 2 valence electrons. So if we were to take these 2 away, it would be isoelectronic to helium, very similarly to what we did with lithium. So let's take a look and write it up. So if it loses those 2 electrons, it'll be +2. That's the only option for it, because that's the only thing that it can do. It can just become +2. It's not a transition metal. So it's going to be +2. And the reason for it, again, is going to be it's more stable. And it's isoelectronic to helium. Because we have helium here. All right, so that's going to be beryllium. Okay, now things are going to get a little more interesting. So now we're in group 3. This is the first group in the transition metals. So we have scandium. Let's do our shortcut electron configuration. So the noble gas that comes before it, this is 21. So the closest one before that is 18, which is argon. And then we have 4s2. And then we have 3d1, okay? So that's the electron configuration for SC. So the orbital diagram is going to be 4s up, down, and then 3d up. Now that we're dealing with the Ds, there's a couple things to think about. One, the Ds either like to be completely gone, so you want to get rid of all the electrons, or they want to be half filled or completely filled. And this year, the only thing that we can do is, if it's completely filled, I'd say leave it alone. If it's almost half filled, meaning it has more than half, so like it has like 6 or something, you'd lose a couple to get it down to half. But in this situation where we only have 2 here and then 1 here, what you would do is you would lose those 3 electrons. So you would get rid of these and these. And so let's talk about why that's going to happen, all right? So first of all, it's +2 if you lose these valence electrons. If you just do this, it's +1. So these are the possible charges, all right? And if you combine them, it's +3. Now, what's the most complicated one that still follows all the rules? That's the +3. Okay, so how do we get it to be +3? What's the reason for this? First off, it's more stable. Okay. The +2 was the loss of valence electrons. The +1 is the loss of the d orbital. And this one's really great because once you get rid of this and this, it's isoelectronic to argon. So this is what you'd have for your reasons, okay? And pretty much everything in this group will do the same thing. They'll all be S2D1. So you can get rid of them. They'll pretty much always become +3. All right, that's kind of the general trend for this. All right. Okay, next up we have Ti, titanium, number 22. So here, the noble gas that comes before it is argon. All right, because it's over here, it's 18. Then we have 4s2. And then there's 3d2. Very similar to the last one we had, right? So let's do the orbital diagram. And this is just 2, okay? So for this, we could have it be +2 for 2 reasons, right? It could be +2 for loss of valence electrons. It could be +2 because you lose the D. Or you can combine them, which is still okay, to get +4. You can go all the way up to +7, all right? So this is probably what's going to happen, this +4. It's the most complicated, but following all the rules makes sense. So that's going to be the one we're going to go with. All right, let's give it some reasons. So loss of valence electrons, and then loss of d orbital. And once you get rid of all of these, it's isoelectronic to argon. So all of this makes it more stable. All right, and that's how we do titanium. And again, pretty much everything in that group is going to do something similar. All right, let's try the next one. We have V. I think that's Vandium. Argon is still the noble gas that comes before it. 4s2, 3d, 1, 2, 3. All right, similar to the last one. And this is up, up, up. So here we have 5, right? We can get up to 5. So how do we get 5? Plus 2 from this, and then plus 3 from losing the D's. Grand total would be 5. Is that possible? Yeah, definitely, right? It's less than 7, so that works. What are the reasons for this? Loss of valence electrons, loss of d orbital. Because you're going to lose all of this isoelectronic to argon. All these reasons are still the same. It's more stable, all right? So everything's going to be the same with Vandium. All right, now let's go to chromium. All right, so here's chromium. Now, chromium is a little bit weird, right? Because it's an exception, and so is number 42. So this would be Cr is going to be argon. But remember what it's an exception for. If we're looking at this, it's normally going to be argon, 4s2, 3d4. But if you remember, this is going to go 4s1, 3d5, because it does that switch to fill up the d orbital, okay? And so its orbital diagram would look like it'll look like this, where it's all half filled in here. Remember, D's really the only one we're going to see that does this year. Don't do this with the P's, okay? They don't shift. The F's do, but we're not even dealing with them this year, so it's okay. All right, so now we have this. And some possible charges are +1, getting rid of this. +5, getting rid of the D's. Or +6, we can do that as well to get rid of all of them. And if you do +6, still following all the rules, it's the same reasons. It's going to be loss of valence electrons, loss of d orbital, isoelectronic to argon, more stable. Same thing, all right? That's the same reason for a lot of these, all right? For a lot of these. All right, so right now, let's recap. We have scandium, +3. That's the best charge we came up with. Titanium, we said +4. Vandium, we said +5. Chromium, we said +6. All right, you see this trend? So as you move across, you're getting +2, +3, +4. Oh, just kidding. Can't count. I should have started at 3. So we have +3, +4, +5, and +6 for these. Okay, manganese. Manganese is argon still. 4s2, 3d, 1, 2, 3, 4, 5. All right, so manganese. Now we have this. Let's do the orbital diagram. Oops, 4s up, down, 3d. All right, so now we have 7. So it could be +2 are possible, plus 5 is possible, but plus 7 is also possible. So we're going to go with plus 7, all right? What are the reasons? Well, loss of valence electrons, loss of d orbital. It's more stable. If you lose both of them, it's isoelectronic to argon. So all the same reasons that we have for this one still work with manganese over here, which is going to give us that plus 7. Now, this is plus 7. That's the highest we can go, right? So from this point on, things are going to start changing a little bit, all right? So we can't just say it's going to be isoelectronic. We can't just do all that. So let's take a look at the next one, iron, and see how things change once you get to 26, all right, or group 8. All right, so we have argon. And with argon, we have then 4s2 still, 3d6, right? 1, 2, 3, 4, 5, 6. Argon, 4s up, down. We have 3d, 1, 2, 3, 4, 5. 1, 2, 3, 4, 5, but then there's one more, all right? Okay, so now we cannot take them all away, right? Because then it would be plus 8. We can't do that. So what we're going to do is we're going to remove valence electrons. That's plus 2. If we remove one of these, then it's going to be half filled, which is awesome, right? But we can do both. So plus 3 is going to be our best answer for this one. Okay, let's talk reasons. Loss of valence electrons. All right, loss of valence electrons. And you have to say now it's half filled d orbital. All right, because after you lose this one, then that'll be half filled. Half filled d orbital. It is not isoelectronic, right? Because it still has a half filled d orbital. So then you can just write more stable. Those are the 3 things you would need for this one. All right, and as we move across, they're going to be similar, but let's see what happens, all right? Next up, we have cobalt. So cobalt is going to be all right, so we have cobalt next. So cobalt's going to be Ar. Let's see, 4s2, right? That doesn't change. 3d, 1, 2, 3, 4, 5, 6, 7. Orbital diagram is going to be argon. 4s up, down. And this is going to be 3d7. Okay, so plus 2, right? Loss of valence electrons. Plus 2, half filled d orbital. Plus 4 is both. So plus 4 is going to be our better answer, right? Plus 4, but it's going to be doing both of those things. What do you write down? Loss of valence electrons, same as the last one. Also, half filled d orbital, because if you get rid of these 2, then it's going to be half filled, and finally, it's more stable, all right? So iron, cobalt will have similar reasonings, just have to make sure you have the right charge for them. All right, let's check out nickel. Nickel, we have argon. We have 4s2, 3d, probably 8, right? 1, 2, 3, 4, 5, 6, 7, 8. Yep, all right, cool. All right, we have 4s2, 3d8. Let's talk charges. Loss of valence electrons, right? Loss of these d's, so it's half filled. But what's it going to want to be? Both of them. All right, now what are the reasons? The same as this, right? Loss of valence electrons, half filled d orbital, more stable. So same reasons for all of those. All right. Now we're going to jump to copper. And with copper, same thing, we'll have argon, 4s. Now this is an exception, right? Let's check this out. We have, normally it would be 4s2, 3d9, right? But we know that these ones have an interesting little kind of switch, right? So with these ones, it's going to be 4s1, 3d10. All right. So with these, you can do a couple things. Let's take a look at this. Now, you can say possible charges +1. You can also, because that's losing the one valence electron, right? You can also say that it could be +5 to make this half filled. But remember, the D's want to be completely filled also. So you can do both of these things, making it +6. But in this, it's like a choose your own adventure where you can actually choose your own adventure. You would get full credit if you went with +1 or you went with +6. But you have to be specific in your answer. You still have to talk about the valence electrons and the d orbitals for both of them, all right? So let's do +1 first. This one would be loss of valence electrons as usual. Okay, but you also have to say that d orbital is completely filled. All right, and more stable. You always have to write more stable. All right, so this is for +1. And this is acknowledging that you understand the two things that are important. One, the loss of valence electrons, but you also understand that a completely filled d orbital is good, all right? Now, if you want to go with +6, you can totally do that as well. So for this one, you still say loss of valence electrons, and then you have to say half filled d orbital, more stable. And for us, for this year, either of those is fine for copper. Either of those is fine for gold too. But there's only one answer for silver. Silver is an exception, right? It's always +1, which means you have to go with the +1. And not only in that, but if this was silver, you would also have to say that silver is an exception. It's always +1. You have to tell me that you know that it's always +1. All right, so in your reason, you would say for silver, loss of valence electrons, completely filled d orbital. Silver is an exception. It's always +1, and it's more stable. All right. So all of that would need to be in there for silver. Okay, here we have zinc. And if you remember, zinc's part of that backwards L. So zinc is always going to be +2 along with cadmium. So when I go through this, just remember that it's an exception. So that's the only option we can have for this, all right? When you get to like mercury or, this isn't going to be on the test. But if you had mercury on a test, then you'd have some more options because that doesn't have to be +2. So let's look at zinc. Zinc is going to be argon, 4s2, 3d10. So it's going to also be 4s up down. All right, so we get 4s2, 3d10. Remember I said it's an exception, so it always is going to be +2. So you got to remember that. It's the only option. All right, and in your explanation, you have to write that zinc is an exception. It's always +2, loss of valence electrons. All right, and that makes it more stable. All right, so that would be our answer for zinc. All right, now back to the top. So we have the last group over here to do. We have boron first. So boron's going to be helium, and it's going to be 2s2, 2p1. Okay, now, a couple things about this group. One, aluminum's always +3, right? It's an exception also. But anything down here this can be considered a transition metal, okay? So if these pop up on the test, you can lose electron, you know, just like a normal transition metal would do. So just keep that in mind, that these things could be plus something, all right? But when you're above the staircase, besides boron, besides this one, because this is going to be positive because there's only 3 here, the rest of them, they're usually going to become negative. All right, so let's talk about this group. Because again, boron, it's in this group where we're going to say it's plus 3 along with aluminum. Let's talk about why it's plus 3. All right, so we have helium, 2s2, 2s up down, 2p up. All right, so we have 3 here, right? So what's going to happen is it's going to lose these 3. So it's going to become plus 3. And the reason for that is then it's going to be isoelectronic to helium. Okay, so by losing these 3 electrons for either boron or aluminum, it'll become isoelectronic to the noble gas that comes before it. All right, and I'm running out of time, so I'm not gonna write down the reasons, but I'll tell you. Okay. Okay, the next one, carbon and silicon. We did these in class. This was plus 4 or minus 4. All right. So with these, it's going to be He, 2s2, 2p2, and then we have helium, 2s up, down, 2p up, up. All right, so this is its electron configuration, orbital diagram, and you can go either way with this. You can take all these away, and then it would be isoelectronic to helium, or you can add 4 more to it, and then it would be filled, and so then it would be isoelectronic to neon. All right, so those would be your reasons for those. All right. What did I do? Oh, you know what? I didn't even notice. It's neon instead of carbon. All right, so we went over carbon again. No big deal. All right, I'm going to clear this, and then we're going to go over nitrogen. All right, nitrogen. This is He, and then 2s2, 2p, nitrogen's 5. Nitrogen's 3, because the total's 5. Helium, 2s up, down, 2p up, up, up. Okay, so as I said before, helium, there's 5 electrons in its valence shell. So if there's 5, it only needs to have 1, 2, 3 more. So nitrogen is going to become -3. And the reason it's going to become -3 is because then it'll be isoelectronic to neon. All right. So once nitrogen becomes -3, it'll be isoelectronic to neon. And oxygen, very similarly, it is He, 2s2, 2p4, He, 2s up, down, 1, 2, 3, 2p, 1, 2, 3, 4. All right. It just needs 2 more. All right. So that's why this group is -2, because it's going to just need 2 more to then become isoelectronic to neon, and that's its reason as well. And last, the fluorine group. All right. So here we have He, 2s2, 2p5. This one just needs 1 more to fill up, so then it looks like neon. So this would be isoelectronic to neon if you made it -1. All right. So for these last ones, these are -3, -2, and -1. And that's basically everything up until the little staircase. So for all of those, -3, -2, -1. This year, there's no options for them, okay? If you get into advanced chemistry, you might learn some different things about them. But for this year, that's all you need for this test.